So, as we studied last time, this it was method 1. Now, currently we are going to involve ourselves in the method 2. So, let me briefly state the result what we did last time. So, because we need that result in order to see what's going on and how the second method was discovered, basically. Every equation in classical mechanics is nothing but a pure observation. It arises by some kind of manipulation, yes, but that doesn't make it less accurate in nature. You need to understand this. This is a fact, and this is the essence of classical mechanics. So, now the derivation of the equation in the form. So last time we got the equation which was r is equal to 1 over u is equal to r naught 1 plus epsilon cos theta or plus minus. We got the two equations. We have one around the vertical and one around the horizontal. So this was a result, the brief result. So the derivation of the equation, let me do it in this form. Okay, there is no laws of generality over here. I'm just taking the the horizontal axis term. So I'm just trying to keep it one at a time rather than confusing. Now, if you see this equation, it suggests that the equation of motion that we are out to find can be manipulated to obtain a simple differential equation. I know it's not evident from viewing this equation, but if you see more carefully, it do give rise to a simple differential equation which has to be manipulated. In order to get those results, we need to manipulate our equations. So we simply start with our force equation, our force law, Newton's second law, provided the mass is constant. Alright, so as I told you before, that this is minus g and 1 and 2 upon square r cap. So this is a conservative force, and it is the negative sign defines that it's an attractive force. It's towards the center, which is nothing but basically the definition of central force motion. Secondly, the mu defines the mass. Now the acceleration has to be written in the polar coordinates. So, but the catch here is we only have r cap term. So let me write and show you. R cap plus a theta cap. If you equate this equation, we don't have any corresponding theta cap equation onto the LHS side, right? We don't, in LHS, in this side, we don't have any equation that corresponds to theta cap. Basically, I can write it as, alright, 0 theta cap equal to mu r cap plus a theta cap. If I equate my theta component vanishes. See, theta cap, I get a theta is equal to 0, right? That means there is no acceleration in terms of central force motion when we consider the plane polar coordinates along the theta cap direction. So by equating the radial component, we get 2 upon r square r cap is equal to mu, and r cap can be written as dr square minus d theta square r cap, right? This is our equation. Now what I can do is, this is basically the radial acceleration in the plane polar coordinates. So setting the components equal, by setting this component equal, which appears as it is in, with the substitution of L is equal to mu r square theta dot. If you remember, we had derived this equation long back in second video, dt, which is theta, right? So get an equation over here by using this dr square t square is equal to L square upon mu r cube. Okay, what I did is to use this zeta dot equation over here, nothing more of a magic or some sort. I'll take this, I keep this side, I'll just bring it to here so that equation is a negative sign, it goes there, it makes a positive sign, that's why there is a positive sign over here, or you can say there is no negative sign over here on r square. Alright, okay. I will write this equation again so that it will be easier for me to take a continuous step. Square upon mu r cube minus g m1 m2 upon r square. Let's box this equation. It's important for us. Now, what I'm going to use is use the same substitution as we did it before. We use the u is equal to 1 upon r substitution. But before that, I want to make sure that my components are not in this form. I mean, not exactly in this form, but the time dependent. Alright, I don't want t dependency. I don't want the t dependency. Okay, so what I'm going to use is I want to change the independent variable. These are independent variable, right? So change the independent variable from t to r. Alright, I want t dependency. I have discussed why we don't want t dependency at length. So dr by dt can be manipulated as dr by du by dt, right? But I can further insist the theta term so that I can use this equation. Now you see how I'm collectively writing the equations, right? You can see it, dr by du by d theta by dt. Just a simple manipulation of this differential equation. I can use this term. Alright, so now I'll use mu is equal to 1 by r, du by dr will give me minus r square. So I have this equation, so I can write my dr by dt term as minus 1 over r square, u square, right? As we are using the u dependency, and du by d theta is an unknown equation, but I do know this term, it's mu square upon mu, which mu square upon u. See, I'm confusing myself. Please be careful when you use such kind of notation. I know it's confusing, but you can't just deviate from the standard notations because they are used throughout our throughout the literature. So minus du upon d theta L. So What have I done?